All right, we are starting ionic bonding, and this is going to be probably the next 3 weeks or so. We have two different types of bonding. We have ionic that we'll do first. You may have learned this in junior high. Do you remember what the other kind is called? It starts with a C. Covalent. And it has to do with how the electrons are arranged or divided up between the atoms. That's the difference between the two kinds of bonding. We're going to focus on one at a time. We'll test on each kind separately, and then we'll talk about some similarities and differences between the two kinds. So we're starting with ionic bonding. And the picture that's on here is a picture of a very common ionic substance, or very common ionic crystal. And we're going to use that as our first example of what ionic bonding is, or what bonding is in general. So if you look at the next picture, you can probably tell me what this is.
Salt and pepper.
Okay, just going with the salt for right now. What's salt made of?
NaCl.
NaCl. So those two things, sodium and chlorine, have to be bonded together. And when you make a bond, you have a combination of atoms, and you form a compound. We should know what a compound is from way back at the beginning of the year. What we might not have thought about before is that that compound has different properties than the original elements that you start with. Two weeks off, you've forgotten how to write things down?
How do you write
Question? They do. I don't know that it's part of the chemical formula. I think it's just something that they mix in with the salt. That might be part of the chemical formula. They do that to help people not have a deficiency of iodine, because we don't get a lot of iodine in our diets naturally. I forget what illness that causes. Something that goes with that. Anybody want to look it up on their tablet? What happens when you have a deficiency of iodine? Yeah, if you can get the internet to work. But they put that in there on purpose. And you can actually buy salt in the grocery store that doesn't have it in there. You can buy salt that has iodine in it too. If we were just to look at pure sodium chloride, pure salt, sodium and chlorine, you put them together. What do we know about sodium by itself? Do you remember from last semester? What are some properties of sodium? It's an alkali metal. What's it do when you put it in water?
Reacts a lot.
It reacts a lot. It does eventually dissolve, but in the process, what do you see? Bubbling. You don't remember? I put it in a dish. It kind of explodes. Sometimes it sparks. Sometimes it sets itself on fire. Okay, so sodium, when it's by itself, when you put it in water, not such a nice reaction. Burns, sparks, runs around the dish, sets itself on fire. What about chlorine? What do you remember about chlorine? It's a gas.
It's a halogen.
It's a halogen.
It goes in your tools.
Yeah, we use it for disinfectant.
React.
Remember what chlorine was maybe the first of its kind to be used for?
Chemical warfare.
World War I. Yeah, it was a poisonous gas. It was one of the first chemical weapons that they used. So if you breathe in chlorine, pure chlorine gas, it's poisonous. Enough of it will kill you. So you take these two elements, which by themselves aren't very nice. Sodium that explodes in water. Think about what most of your body is made of. and chlorine, which is poisonous enough to kill you. And you put the two of them together, and what do you get? Salt. Do you eat salt? All the time. Well, it's in your food, right? So, this is a good example. Listen, please. This is a good example of how elements by themselves have very different properties than the compounds that they make when you put them together. You take two of the most dangerous elements, arguably, from the periodic table, you put them together, and you get a compound that's in your food. You consume it every single day. And it doesn't explode when you eat it, and it doesn't kill you when you swallow it or ingest it. So compounds have very different properties than the elements that make them up. And part of the reason that we make compounds, that we have compounds, is because of the electrons. And this is going to go back to our electron configuration stuff that we talked about last semester too. And did you find it, Danielle? So what is it?
It says that you can get constipated, depressed, dry skin, fatigue, and goiter, sensitive to the cold, menstrual cycle abnormalities, protrusion of the eyes, thickening of skin, brittleness of hair, nails, unintended weight gain, and weakness.
That sounds like not such a nice list of things.
It says you can also get irritated or suicidal, bleeding while pregnant, change in the level of consciousness or alertness, mental status change, chest pain, tightness, pressure, palpitations, and respiratory problems.
Yeah. Make sure you get your daily intake of iodine. Okay, so background information. Why do atoms bond in the first place? Why do we get compounds? It has to do with their electrons. It also has to do with how stable they are. You probably have an idea that some elements are more stable than others when they're by themselves. For example, sodium that we just talked about is not very stable when it's by itself. It's never found pure in nature. We know that from last semester. It reacts violently with water, so it's probably not going to be found by itself on our planet, which is mostly water. So atoms will bond with other atoms to increase their stability, make them less reactive or more stable. In the process of doing that, they also decrease the amount of energy that they have. And when we talk about decreasing the amount of energy that they have, we're talking about potential energy. And potential energy is the chemical energy that's stored inside of a chemical bond. When an atom bonds with another atom, it has less energy than it did before. This idea of changing the amount of energy in an atom goes along with something that we talked about at the very beginning of the year. Do you remember what BARF stands for?
Breaking bonds absorbs energy.
Yeah?
Releasing bonds forms energy.
Said the second half backwards, but you got the words right. When you break bonds, energy is absorbed. And remember, we labeled that kind of process endothermic, energy in. So these are the 2 bullet points underneath your acronym there. When bonds are broken, energy is absorbed. That's an endothermic process. Energy goes in to break bonds apart. And what we've been talking about so far, bond formation or forming bonds means that energy is released and and that would be an exothermic process where energy is released or let out. This idea of whether or not bonds are being formed, energy is released, bonds are being broken, energy is being absorbed, you can describe as just bond energy. And that would be the energy that's required to break a bond, or the energy that you get when you make one. We could actually put a number to this. If you go on and take college chemistry, you probably will. They actually have numbers or amounts of energy that they say are bond energies. Every different compound, every different combination of atoms has a different bond energy. For us though, all we really need to know at this point is that the higher the bond energy, the more stable the compound. So if you have a higher bond energy, that compound is not likely to break apart, or it's going to take a lot more energy to break it apart. So the more stable it is, the higher the bond energy. I've already introduced this idea once today. There's more than one type of bond between atoms. In fact, there are probably three major categories that we're going to look at. Two big ones and then one that's kind of smaller. One of the main categories of bonds is called ionic bonds. And those are the ones that we're going to be focusing on for the next 2.5 to 3 weeks. Ionic bonds are caused by an electrostatic attraction between oppositely charged ions. What does that mean? What does electrostatic kind of sound like if you switch the order around a little bit? Static electricity. Static electricity is very much the same as an electrostatic attraction. You get static electricity like on your clothes or in your hair when you get one charge built up on one thing and the opposite charge built up on the other. You bring those two things together and you get a shock. Same kind of idea with these atoms. One has one charge, one has the other. Kind of like Colton said with the magnets, what opposite things do? Attract. So then you get an attraction between something that's positively charged and something that's negatively charged. Do you remember what ions are? Yeah, it's a cation.
It's a atom
Atom that has lost or gained an electron.
Great, perfect. It's an atom that has a charge, an atom that has either lost or gained an electron. So something that has lost an electron would have what kind of charge? Positive.
And that'd be a cation.
And that would be a cation. Very good. Something that has a negative would have gained an electron. Do you remember what those are called?
Antions.
You're close. Anions. Anions. So you have to have a cation and an anion to make an ionic compound. That kind of makes sense. So compounds are formed by the attraction of cations to anions, something that's positive to something that's negative. idea is one of the keys to understanding how to predict which things are going to make ionic compounds or what compound is going to be formed, because you always have to have a positive thing attracted to a negative thing. So when you're deciding what elements will be involved or how many of those elements you need for that compound, you always have to have a plus and a minus. Overall, ionic compounds are neutral. That means they don't have a charge when they're in a compound. If you think about table salt, NaCl, which was our example, it doesn't shock you when you eat it. It doesn't have a charge when it's in a compound. So that means that the total positive charges in that compound have to balance out with the total negative charges. This is kind of like a little math lesson. If your total positives have to equal your total negatives. If you have an atom that's a +1, then you have to put it with an atom that is -1. If you have an atom that's a +2, then you have to put it with -2. Now there's different combinations that you can use to make those two things equal out, but your total positives always have to equal your total negatives. They have to add up to 0 so that your compound doesn't have a charge. This kind of bonding, where you have a positive ion and a negative ion, occurs between mainly two different kinds of elements. You have to have a metal and a nonmetal. Where do you find the metals on the periodic table in general? Which side? Middle to... middle to the left. Where are the nonmetals located?
To the right.
To the right. So if you're going to be making an ionic compound, you usually have to pick something from the left and something from the right. Those two things have to go together. One of them will be positive, one of them will be negative. There's one kind of exception to that. You can also pair up a metal and a polyatomic ion, and that's something that we haven't talked about yet. What does it sound like though? What's that prefix mean? Like a polygon means multiple something. So polyatomic would be multiple atoms, and you already told me what an ion is. An ion is something with a charge. So a polyatomic ion is a group of atoms with a charge. And we'll talk more about what those are as we go through ionic bonding stuff. For today, the big idea is that you need a metal and a nonmetal. You need something that's positive and something that's negative. Some examples of things that are ionic compounds. NaCl we already listed. Which part of that is the metal, by the way? The sodium. Magnesium oxide. Magnesium is the metal. Oxygen is the nonmetal. And then the last one, NaHCO3. Any idea what that is? Guarantee that most of you have it in your kitchen. You're close. It's baking soda. And sodium bicarbonate is what that's called. So what part of this is the metal then? The sodium. And then what do you suppose this mess of stuff is over here? A polyatomic ion. Very good. HCO3 is a polyatomic ion. So there's an example of one of those new ions that we haven't dealt with before. Okay, so last thing for this section, and we are going to keep going just a little bit into the next section. Last thing for this section is, what are some properties of ionic compounds? In general, what are ionic compounds like. Most ionic compounds will be in the solid state at room temperature when they're pure, like salt. And when they're in their solid state, they have a crystalline structure. Something that has a crystalline structure. We just barely touched on this last year in Earth Science, but if it has a crystal structure, then all of its atoms have to be nice and neatly arranged in orderly patterns. Usually has some kind of geometric shape to it, like a cube or maybe a hexagon. We looked at some things that had crystalline structure last year in Earth Science. I think we looked at pyrite, maybe, fool's gold, and probably some quartz. Quartz has a hexagonal or a six-sided crystal structure. Most ionic compounds have that kind of crystal structure. So if you think about all the minerals that we looked at last year, Earth Science is going to start that here pretty soon in a couple weeks. Most of those minerals we saw were ionic compounds. So we could have written a chemical formula for those. And another thing you might remember about minerals is most of them are pretty hard substances, and they tend to be brittle. If you smacked it with a hammer, it would probably break into a bunch of different pieces. One thing that you may not know, might be new, about ionic compounds is that they have a very high melting point. What do you suppose a melting point describes? When it melts. Yeah, what temperature does it melt at? What's the melting point of ice?
32 degrees.
32 degrees Fahrenheit or 0 Celsius. That's a pretty low melting point, all things considered. If you wanted to melt salt, for example, you would need 801 degrees C. What's the temperature that water boils at in Celsius? 100, just plain 100. So boiling water is 100 degrees. If you want to melt table salt, you have to have 8 times that. That's pretty hot. It's not going to happen on your stove at home. Most ionic compounds have a pretty high melting point. Most ionic compounds do not conduct electricity as solids. If you hooked up a battery to a salt block, it would not conduct electricity. However, they do conduct electricity as liquids. So if you could get them hot enough to melt, then they would conduct electricity. They also conduct electricity as solutions. What does that mean you've done with it?
So like you
Dissolved it in water. So if you put salt in water, then the solution will conduct electricity. Okay, we've got one more thing to add there. Some of you flipped your page already. We've got one more thing at the bottom to add. Add a little bullet point if there isn't one. The last thing that we need to talk about with ionic compound properties is that ionic compounds do not form discrete molecules. Instead, we have something called formula units. So I'll let you write that down and then we'll talk about what that means. So, what does that mean? Not discrete molecules. What's a molecule? From last semester, what's a molecule? A group of that are
Get it.
bonded
Yeah,
together. A group of atoms that are bonded together. For example, water is a molecule that most of us are probably familiar with. If you wanted to make a water molecule, what atoms would you need? Hydrogen and oxygen. How many of each? 2 hydrogens and 1 oxygen. And once you made a water molecule, 2 hydrogens, 1 oxygen, it would be its own entity. Its own separate little entity. Yeah, it sounds kind of funny. But a molecule is a group of atoms that's bonded together, but it's a separate thing from the molecule that's next to it. Compare that to, it's going to be a little bit of a stretch here, but compare that to a toy that probably most of you have played with, Legos. Until you run out of Legos, is there any limit to how many pieces you can click together? No. Ionic compounds are a lot more like Legos. You could make an ionic crystal as big as you want until you run out of pieces. So you just keep clicking them together. So what's a formula unit then? A formula unit is the smallest ratio of those things. So if I wanted to make a salt crystal, for every sodium I would need a chlorine. I have to have 1 and 1, right? Because that's what the formula says, NaCl. So for every sodium I'd need a chlorine. But if I wanted to make a giant salt block, like to put out for deer or something, I just need a lot of pieces. Sodium, chlorine, sodium, chlorine, sodium, chlorine. And you keep going until you get the size of crystal that you want. So ionic compounds are a lot more like Legos. Molecules are their own separate little things. Okay, we've got just a few minutes left. We're going to go ahead and start the other notes just briefly. We won't get very far. We will end up finishing these tomorrow. One of the things that we can use to help decide which items are going to bond together, which elements to put together, and how many of them should we have, is called a dot structure. A dot structure is a visual representation. This is the bullet point right at the top of the page. A visual representation of valence electrons. Uh-oh, more things to remember. What are the valence electrons?
Leftover electrons.
Almost.
They're all the highest energy level.
Highest energy level. They might be unpaired, but not necessarily. It's the highest energy level electrons. These are the ones that are on the outside of the atom. If there are electrons that are going to be involved in bonding, like either lost or gained, it's the valence electrons that are going to be involved. So a dot structure is a picture that shows the valence electrons. What symbol do you think we'll use to represent electrons? What's this called? Dots. Dot structures. The idea behind these pictures is based on having a stable octet. We talked about this last semester. Do you remember what that means? Octet is how many? 8. 8's the magic number. Once an atom has 8 electrons, then it tends to be more stable, and it's not quite scientifically correct, but it's like a happier atom.
Where do we write it?
You could put it right at the top there. And then underneath your table, we have a space for the Octet Rule. The Octet Rule says that atoms and compounds tend to have the electron configuration of a noble gas. And we kind of talked about this right before Christmas when we talked about how you make a cation or how you make an anion and why an atom would want to make a cation or an anion. We talked about what would be easier, to lose so many electrons or to gain so many. And I think that'll be our last thing for today, so we'll go ahead and stop there. There is no homework. We will finish these notes tomorrow.